All right, friends, here we are in semester college algebra. We're going to go ahead and go through our first lesson today, which is going to be a review of some of the more basic algebra concepts from earlier algebra classes that you've taken. So this is what we're going to call Chapter P for prerequisites, and you can see here is the basic plan for the next 3 days. I told you guys in class that the pace of this class goes very, very quickly. So this video might be a good indicator on whether or not this pace might be something that you can handle, okay? But you guys can see that in this video, we're going to go ahead and take a look at P.1 and P.2, start to talk about real numbers and their properties, and also get a little bit into exponents and radicals, so let's go ahead and dive into that, all right? So we're going to start off with P.1. and just kind of review some things about your real numbers and your properties. So first of all, when you talk about your real numbers, we like to kind of always think about them in terms of an order on a number line. And so we could start to talk about sets of numbers by talking about where our set begins and where our set ends, and then discussing whether or not we include those two numbers themselves. So there's a couple different ways that you can point this out, what we call an interval, which is just a subset of the real numbers. First of all, there is interval notation. Interval notation involves the use of parentheses and square brackets to emphasize our beginning number and our ending number where our set begins and ends, and then whether or not we're including them. So it says here parentheses are used with open circles on the number line. So it would be a number like where my set begins, like here at the number 2, you can see I have an open dot there, and then a bracket is used to indicate that I am including that number in the set that I want to talk about. Okay, so that's where I end. So the notation for interval notation here is that I begin with 2, I end with 5, I want everything in between, and I don't want to include 2, so parenthesis, but I do want to include 5, so square bracket. Okay, that's how that notation works. I can say the exact same thing by moving on to inequality notation, which says, like I said, the exact same thing, just using different symbols. So using your less than or your greater than or less than or equal to or greater than or equal to symbols, we can convey the same idea, just that set of numbers between 2 and 5, not including 2, but including 5. We could say that using these inequality symbols right here. Specifically on this one, since it is less than or equal to, that does tell me that I am including that value of 5 in my interval, okay? And also there's the, might be the easiest way just for purposes of communicating, which is just the simple verbal description. What we mean to say here is just all the real numbers greater than 2, but less than or equal to positive 5, okay? So anytime you want to talk about a subset of real numbers, that's what we call an interval. There's a couple different ways that you could point that out. Now here on this next page, there is this difference between an interval being bounded and unbounded. Okay, so unbounded means just that. It means it doesn't have a bound on one end or maybe on both ends. So that is going to mean that we have this notion of going out to either positive or negative infinity whenever we have an unbounded interval. If we have a bounded interval, that means we have a definite starting number and a definite stopping number, and then it's just an issue of whether or not we're including those values. So here on this interval, I'm going to have two values, A and B. I begin at the value A, and I end at the value B. So what I might do here, just to start us off here, is go ahead and include those two values on each one of these number lines here. And then we might talk about how to represent these graphically. So in that first case where I have just two square brackets, remember that square brackets mean that I am including those values. So what that's going to mean for my graphic notation, my number line graph, is that I want to include some solid dots on those values because I'm including them. And it will go the same way anytime you have a bracket. So as you scan through your list, this second one right here doesn't have any square brackets in it, so we're going to instead have some open dots on those values. Again, open dots means if it doesn't get shaded in, we're not including that number. The third one down has a bracket on A, so that means that I do want to include that number A in my interval, but I don't want to include that value B in my interval, so we're going to have an open dot on that value. And then just the reverse on the next example down, this is the one where I want to include B, but not A. And then in each one of these, this interval notation means to suggest that not only do we want these two values, we also want everything in between. So for that reason, I'm just going to go through on each one and simply do some shading in between there just to signify that, graphically speaking, we want all the numbers that are between these values here. Okay, so those are bounded. It has a definite starting number, a definite stopping number, and then just whether or not we're including them is important to note. On the unbounded interval, again, this is where we either go out to positive infinity or to negative infinity. So because we have a definite start number on each one of these, I'm just going to go ahead and mark it on my number line here real quick. So this first one talks about this number A, and so does the second one. The third one and the fourth one talk about this number B. So we'll mark that on my number line here really quick. And then let's go ahead and signify whether we are including these values or not. So anywhere we have a square bracket, that's including the number. So we'll put a solid dot there. So it looks like that's the case in the first one. Looking for more square brackets, if you go to the third one down, it looks like I see another square bracket there on B. So I'm going to go ahead and include a closed dot or a filled-in dot on that. These other two here, the second one and the fourth one, those just have open parentheses. That means open dots on those values to signify that we're not including those values. And then let's just talk about what we mean to say as far as what numbers we want to shade, right? So in the interval notation on this first one, if I zoom this in really quickly, it says to start at A, but then to quote-unquote end once I reach positive infinity. So this is the set of numbers that's going to start at that number A, and then I want all the ones that go from A all the way out to positive infinity. I could say that in an inequality notation by saying I want all of the numbers, which is what this X represents, I should say. This just means to say give me all numbers, X, such that they are greater than A or also equal to A, okay? So how do we represent that graphically? Well, if I want to be greater than A, then that means I'm going to the right of A. So that means I'm going to shade my graph to the right, okay? Very similarly on that next one, it's just basically the first and the second examples here are almost identical. It's just a matter of whether or not we are including that value of A in that interval we want to talk about. Okay, so notice the subtle difference there. One has a filled-in dot while the other has an open dot, and that's because of the notation over here in your interval notation. One's a bracket and one's a parenthesis. So just different ways to communicate these sets of numbers. Going down to the third and fourth one, now we want the set to quote-unquote start at negative infinity, and we want to go all the way until we end at this number B here. Okay, so of course, that's going to mean that we're going to shade to the left of B because that's where my negative numbers live. And as I keep going further and further to left, I'm going to keep approaching negative infinity more and more. Okay? Same thing on that one down below. Again, it's just a matter of whether or not we are including that value. Very similar graph there. And then this very last one, let's talk about this, right? Because, again, interval notation works in this way. We start at the number on the left and we end at the number on the right. And it's a little bit misleading to suggest that we can start at an infinity because we'll never reach it, but that's the idea here, okay? Basically, this is all real numbers is the idea that we want to convey. If I'm going from negative infinity all the way to positive infinity, then that means I just want all the numbers on the real number line. So I would just shade this whole thing and not worry about open or closed dots whatsoever on this example, okay? And you could check the inequality notation too. Basically, again, anywhere you see X, that just means all numbers. So that inequality notation is meaning to say, give me all numbers that are between negative infinity and positive infinity. Okay, so these are just different ways to communicate intervals of real numbers. And so let's go ahead and get to some examples here. So it says, verbally describe each inequality, sketch it on a number line, and then state whether the interval is bounded or unbounded. Let's answer that last question first because it's the easiest. Basically, again, unbounded means that I either have negative infinity or positive infinity in the mix, okay? If you look at both of the examples that we have here, I don't see infinity at all, so that means that both of these intervals are bounded intervals. Actually, let me take that back. Because while we don't see infinity, remember that infinity will only show up in your interval notation or maybe in like a verbal description or something like that. So if you look at that part B there, this says X, or in other words, all the numbers that are greater than or equal to -5. Well, there's infinitely many of those, so this would be an unbounded set. So just because you don't see infinity, like I was trying to suggest before, doesn't necessarily mean you don't have an unbounded set, right? You got to pay attention to what it is it actually says and then go from there. So those are bounded or unbounded, and then it says to verbally describe each inequality. So just informally here, I'll just go ahead and say it out loud instead of writing it down. On that first one, it just says -2 is less than or equal to x, which is less than 3. And what we mean to say there is give me all the numbers that are between -2 and 3 on the number line, and include -2, but don't include -3. And I say don't include -3, or sorry, I don't include +3, I should say, because I don't see an or equal to on that inequality sign. Okay, and let's go ahead and sketch ourselves a quick graph of the number line here. We're just going to go ahead and draw a horizontal line. Let's mark where -2 is, and let's mark where 3 is. And the next thing that I'll do after I mark those points is I will say whether or not we include those values, and I'm looking at these or equal to's. On this one, on the -2, I have an or equal to there, so that means I am including that value. So we're going to go ahead and shade in that dot, but on the 3, I don't have an or equal to on that inequality symbol, so that means I have an open dot. And since x is sitting in between -2 and 3 in this notation, that means that we just want to have all of the numbers that are between these two values on the number line, okay? So I will leave you guys to write the verbal description on your own, but that would be how I would think about this, right? For that next one down, let's go ahead and draw ourselves another number line, and let's mark where the number 5 is, or sorry, I should say -5, and then let's go ahead and think about this, right? So now that I've got it marked down, the next thing I'm thinking of is, am I including that value or am I not? Well, again, you got to look at your inequality symbol. It looks like both of these are given to you as inequality notation. So I do see the or equal to on that greater than symbol, so that means that I can be equal to -5, or in other words, I'm including it, and I want to shade all of the numbers that are greater than -5. Okay, so you got to know your inequality symbols. This one happens to be greater than, and so that means, am I going to shade to the left or am I going to shade to the right? Well, all the numbers that are greater than -5 would be to the right of -5 on the number line. So a couple things I'm asking you guys to know, right? I'm asking you guys to know which direction your inequality symbols are. I'm asking you to know the order of the number line, right? So as you go further to the right, you get bigger positive numbers. As you go further to the left, you get bigger negative numbers and that kind of thing. And being able to make a quick sketch like this of a graph with proper notation, filled in dots, open dots, that kind of thing is really important for you guys to be able to do. Next little set here, it says use inequality and interval notation to describe the set. So here we are given a verbal description, and we have to go ahead and represent using both interval and inequality notation. So it says y is at least 21. Okay, so what you want to do is you want to read that idea and think about that on your own in terms of like, what does that actually mean? If I am a number and I am at least 21, then that means that I can be a number like 22, 23, 24. These are all numbers that are at least 21. If you got to put it in terms of like a tangible idea, maybe think of, you know, a basket of apples, if you want to think about it that way, right? If I have a basket of at least 21 apples, then that means that my basket can have 22 apples in it, 23 apples, 24 apples, etc. So that's the idea that we want to convey. We basically want to convey either this idea of I have exactly 21 or I have a number that is more than 21. So in other words, in inequality notation, I would say that I am greater than or equal to 21 apples. Okay, well, what is greater than or equal to 21? Well, they already kind of told us in the verbal description. That's just this variable y that they introduced. Okay, so that will be the way to express that in inequality notation. We also have to do interval. So remember, the way interval works is we have a starting number, and then a comma, and then ending number, and then we just need to say whether or not we have parentheses or brackets to indicate whether we're including those bounds, right? Well, think about how many numbers are at least 21, right? There are infinitely many of them. So what I might do here is I might say that my list will start with 21, and where do we end? Well, there's infinitely many numbers that are at least 21, so really this list never ends. It's going to go all the way out to positive infinity. If I have 1 million apples in a basket, that's at least 21 apples. It's kind of an extreme example, but you get the point, okay? Now, brackets or parentheses. One of the things that you guys need to make sure that you know is that when you have infinity in the mix, no matter what, infinities always get a parenthesis. And again, because parentheses mean you don't include that value, and infinity is something that you'll never reach, so we can't include it. So infinities always get a parenthesis, even negative infinities when those come up. Those always get a parenthesis, okay, not a square bracket. Now, if I want to be at least 21, I can have exactly 21 apples in my basket and still fit this description, right? So that means I'm going to have a square bracket there on 21, and that will complete the interval notation on that, okay? What I might do for this next one is encourage you to pause the video real quick and take a look at that next one. X is less than 12, but no less than -7. And then when you're ready, go ahead and unpause the video and we'll show you what the deal is. Okay, let's take a look at this one, right? So the first thing that it says is X is less than 12. Sometimes these are worded in such a way where it's really easy to indicate what the interval notation would look like, right? So if I want to convey X is less than 12, I'm just going to write that using symbols. X is less than 12, pretty good. But it says here, X is no less than -7, okay? Well, if I'm no less than -7, I need to be greater than -7. So writing it as a compound inequality like that is really, really important to do. And the reason that I'm using just strict less than symbols here and not less than or equal to is because if you were the number 12, are you less than 12? Well, no. Reverse that psychology, right? If you were -7, the number, could you be no less than -7? Well, no, because then you're exactly equal to -7. So for that reason, I'm not going to say or equal to on these numbers. I'm just going to go ahead and leave it like that for my inequality notation. And then for interval notation, I just want to go ahead and simply write where my list begins, write where it ends, and then use parentheses or square brackets to indicate whether or not we're including those values. Well, we just said in the inequality notation that we're not including these values. So we're going to use the symbol that means we are not including either of them, which is a parenthesis on either one. Okay, so inequality and interval notation, very important that you guys understand the difference between those. Okay, so switching gears a little bit, instead of talking about the order of our numbers and how to represent them in subsets of numbers, let's get into actually doing operations with numbers, and specifically doing them with fractions, because so many different numbers out there are represented as fractions. We need to know how to deal with them in terms of adding or subtracting them. Okay. So just really quickly, anytime you want to add two fractions together, this is the thing that you really need to make sure that you have, is that your two fractions have the same denominator. So here that's represented by this value of b. b is the same as b, so we can feel free to go ahead and combine the numerators of these fractions really easily. Down here, if you don't have common denominators, then you're going to have to do a little bit of extra work, right? Because the common denominator would be the one that you get by multiplying those two together. And the only way we're going to get that, like say on this first fraction, is if I introduce a times d on the bottom, which means I need to introduce a times d on the top, which is where I get this AD from. And then same thing for the second fraction. If I want this to be BD, then I have to introduce a B times D in the bottom, which means I have to introduce that same thing to the top. So B times C, and that's why we get BC there. Okay, so that's just finding a common denominator. That should not be anything new to you guys. And adding and subtracting with fractions is really the only types of examples where it's going to be a pain like that to have to combine. Multiplying and dividing are still relatively simple. Multiplying is just straight up multiply the numerators, multiply the denominators. That's pretty good. And division is basically just multiplication by the reciprocal. I'm going to make a note here about that, right? So when you want to divide, you just simply need to multiply by the flipped upside down version of that fraction. That's called a reciprocal in general, but just to save some time in writing, you guys can go ahead and see here that that's what we did. We took the C, we put it down there, we took the D, we put it up there, and we have this new reciprocal fraction to now change the operation from division to multiplication. So multiplying by the reciprocal is how we're going to take care of division of fractions. So here in example 2, we need to perform the operations and simplify. Look at all these denominators. Okay, I've got a denominator of 5, I've got 10, and I've got 15. These might be some that stand out to you because these are all multiples of 5. Okay, so the question is, what can we do to combine all of these denominators into one? Or in other words, find the greatest common divisor, or the, yeah. So anyway, we'll just kind of get into it here, right? So if you think about it, right, you're thinking of numbers that 5, 10, and 15 all go into, okay? So a number that pops out to me is a number like 30. Okay, so what if I took all three of my fractions and instead of having denominators of 5, 10, and 15, I changed them all to a denominator of 30? What would that mean for our original three fractions? Well, here in this first fraction, the 7 over 5, if I want this denominator to be a 30, then I'm going to have to take that 5 and I'm going to have to multiply it by 6, because 5 times 6 makes 30. Well, I'm going to have to do that exact same thing on the top here if I'm doing it to the bottom. So that's going to be a 7 times 6, which for us, that's going to be a 42. So that fraction 42 over 30 came from the 7 over 5, but it has the denominator that we want, okay? Next, what we're going to do is take a look at that second fraction. It's a 10. I want that to be a 30 in the denominator, so I'm going to have to take that 10 and multiply it by 3. Well, whatever I do to the bottom, I got to do to the top, so that's going to be a 3 times 3 in the top, which is going to mean for us that I've got a numerator on the second fraction of 3 times 3, which makes 9, okay? And then finally, for that last fraction, I have a 15 down on the bottom. I really want that to be a 30, and so the way that I can get a 30 from a 15 is by simply multiplying it by 2. But if I do that, I'm going to have to do that to the numerator as well. So that's going to be an 8 times 2, and that's going to be, 8 times 2, goodness, that's a 4 times 2, which is 8. There we go, okay? Now, we have a common denominator in each one of these fractions. The next thing that we need to do is make sure that we combine these in the correct way, okay? So there's this whole business of, do I do the subtraction first or do I do the addition first, okay? The correct answer there is we're going to do whatever comes first as we scan this expression from left to right. So because the subtraction comes first before the addition, that's the one that we're going to go ahead and do first, right? So we are simply going to go ahead and do a 42 minus 9. And if you do that, that's going to give you 33. So we are going to combine these two fractions here, okay? And we are going to be left with 42 minus 9, which makes 33 over 30. And then we'll tack on that plus 8 over 30 and then add those together. Okay, so 33 plus 8 is going to, of course, give you 41. So 41 over 30 is going to be our final answer, and if you check to make sure that that reduces, I don't believe that that will reduce for you, and so we do get this nice little positive result right here. Okay, so that's just a little bit of background on how to take care of one like that. We'll zoom through the rest of these. That next one, 14 divided by 1/2. Remember that if you ever divide by a fraction, that is equivalent to multiplying by the reciprocal. So if we take this fraction, 1/2, and we flip it upside down, then we are going to get 2 over 1, of course. So we're just simply taking 14 times 2 over 1, aka just 2, and so that is going to simply give us 28 in that example. So nice, easy result on that one as well. All right, next one down, we have 8 times the fraction 3 over 6. A couple different options you have on this one, but my biggest recommendation is to always make sure that you reduce your fractions as much as possible if you notice that they can reduce. This fraction right here, 3 over 6, that can reduce to a 1/2. Okay, and if you look at it this way, 8 times a half, well, what's half of 8? That's simply just 4. Okay, so if you start to pick up on stuff like that, then it becomes really easy to do this stuff mentally and quickly. Okay, last one involves variables, so 3x over 7 minus x over 2. We don't have a common denominator there yet, but we have denominators of 7 and 2, so a common denominator that we may want to go with is 14, because that's what we get when we take 7 times 2. Okay, so what is it going to take to make that first denominator of 14? Okay, well, I've got a 7 already. I'm going to have to introduce a times 2 to make that a 14, which means I'm going to have to also introduce that to the top, a times 2. So 2 times 3x is going to give us 6x for that first fraction. And then the operation is subtraction in the middle. Let's go ahead and take a look at that second fraction there. I want that bottom to be a 14, and so I'm going to go ahead and take a times 7 to that denominator, but whatever I do to the bottom, I have to do to the top to keep things consistent. So x times 7, we would write that as 7x. And so here, I've got common denominators now, so I have the green light to go ahead and carry through with this subtraction. I've got 6x minus 7x. That's going to give me negative 1x, or I might just write that as negative x there, and there is my result right there. Okay, so that's going to do it for this first video. This is P.1, and there is an assignment attached to that, which you guys can see right here. Go ahead and get to work on that. There is P.2 to also get through, but that's going to be in the next video after this one. So let me know if you guys have any questions. Thank you very much, and that is going to be it for this video.